In this video, I'm going to show you a couple other techniques that utilizes substitution. So we've already gone over these type 1 and type 2, and here's a type 1 where that's going to be my u, that 4x plus 3. And so if u is 4x plus 3, I'm going to let u be that 4x plus 3, which means du, my differential u, is 4 dx. And therefore what's left is just a 1 dx, so I replace the quantity 4x plus 3 to the fifth with a u to the fifth, and the dx ends up being not exactly du, but a fourth of du. Okay, which you then integrate, 1/4 comes down, u to the fifth becomes u to the 6 over 6, and I get 1/24 u, which is 4x plus 3, to the 6, plus your constant of integration. Okay, so in that particular problem, I had a linear term, and its derivative wasn't exactly dx, but it was a multiple of dx. In this case, it was a fourth. Okay. Here's a similar type problem, but in this case, note we have a quadratic and we have a linear term. Okay. And so I'm going to let u be my quadratic term, because then du is going to be either exactly or a multiple of my yellow linear piece. So I'm going to just replace that through my substitution. 4x squared plus 3 to the fifth ends up being e to the fifth. And the 2x dx ends up being not exactly du, but a fourth of what du is. Okay, and so now I'm able to integrate that. It's a fourth times u to the 6 over 6, which is going to be a fourth times, put my u back in, 4x squared plus 3 to the 6 plus my constant of integration. Whoop, that should be 24. 4 times 6, 24. Okay, so let's talk about another type. And in this type, well, first let's summarize. In each of these two types, you have a function. Here are your two quote-unquote inner functions, and you have either its exact derivative or a multiple of its derivative left over, which allows you to replace the x's with the u's and the x's with a du, or some multiple of du. This particular problem is very different because we don't have that situation. But for this particular problem, we can use substitution to change the variable. So I don't know how to integrate that with x's as it stands. So let's see if I can clean that up a little bit. So if I let u be my 2x minus 1, then my differential u is going to be 2 dx. But what I can also do with my u is solve that for x, if I want to. So if u is 2x minus 1, that makes x u plus 1 all over 2. Now let's see what's going to happen here. Okay, I'm going to substitute my x with this x. So that x becomes u plus 1 over 2. Okay, so here's my x. I substitute it with u plus 1 over 2. Right over here, my integrand. Okay. The next thing I'm going to do is I'm going to replace 1 over root 2x plus 1 with u to the negative 1/2, which is what it is. All right. So my u, if u is 2x minus 1, then 1 over that is u to the negative 1/2. So this essentially becomes this, if u is 2x minus 1, which it is. So the only issue now is my dx, and if I work down here, if I solve for dx from my du, dx ends up being half of du. Okay, so my dx becomes half of du. Okay, so that's my third substitution. Half of du, that's my dx. So I just substituted, and now let's see if that's helpful. So I'm going to multiply. I got a 1/4, I got a half times a half, and then I'm left with a u plus 1 times u to the negative 1/2 du. And I guess I can distribute that. The 1/4's come along for the ride. U times u to the negative 1/2 is u to the 1/2. Distribute that again. And, ooh, now that's not all that clean, but it is a function which I can then integrate using the power rule with a 1/4 out front. So I started way up here with kind of a messy x's and dx integrand, and now I have u's and du's integrand that is integrable. So now I'm going to integrate. So the antiderivative of 1/4 times a quantity u to the 1/2. Well, if I integrate u to the 1/2, I'm going to bump the power up to 3/2. Divide by that new power. If I integrate u to the negative 1/2, the power goes up to positive 1/2. Divide by that new power. Divide by 1/2, multiply by 2. Okay, I'm running out of room here, but let's see if we can finish this off. 1/4 times a quantity 2/3. Now my u is way up here. My u is 2x minus 1. So this u ends up being 2x minus 1 to the 3/2 plus 2 times that same u, which is 2x minus 1 to the 1/2. Okay, all times 1/4, which really ultimately becomes 1/4 times 2/3 is 1/6, and 1/4 times 2 is 1/2. Okay, plus my constant of integration. Now let's check to see if that works. So here's my check step. So I'm going to take the derivative of what I think is the correct antiderivative. So I'm going to take the derivative of 1/6 2x minus 1 to the 3/2 plus 1/2 2x minus 1 to the 1/2 plus my constant of integration, which of course will zero out. And we'll go term by term. That 1/6 comes along for the ride. 3/2 comes down. Times, keep that inner one intact. Bump the power down 1 times by the chain rule the derivative of the inner, which is times 2. Plus this 1/2 comes along for the ride. That 1/2 comes down. Times the quantity 2x minus 1. Bump that power down. Times the derivative of my inner times another 2. And with a little luck, this will turn out to be something nice. So what I get here is, let's see, I get 3/12 times 2, which is 6/12, so I get 1/2 times 2x minus 1 to the 1/2, plus I get 1/2 times 1/2, 1/4 times 2 is 1/2, 2x minus 1 to the negative 1/2. Okay, well, you know what, that doesn't look a heck of a lot like what we want it to look like, but I bet you when I work it out a little bit it will. So let's continue to process this. So let's try to simplify that. And I'm going to take the 1/2 out, and that's a root 2x plus minus 1 plus, and that's going to be 1 over the same thing. Right? Now with a common denominator, this I'm going to multiply by root 2x minus 1 over itself, so it just becomes 2x minus 1 over that common denom. And of course that's still a 1 over here. Ooh, and lo and behold, those 1's cancel. Nice. And I'm left with 1/2 times 2x. Oh, the 2's cancel. And ooh, Yahtzee. Okay, that's exactly what I want. X over root 2x minus 1. X over root 2x minus 1. Bingo.